Hey AP Chemistry, this is coming to you from my house. I'm doing the PowerPoint on chromatography right now, and I just want to say really quickly that this is really weird. Teaching in my dining room, and my document camera's right here, and all sorts of weird stuff's going on. But we're going to get through this. I do not know how long we're going to be like this. To be honest, we are really, really far ahead with AP Chemistry. So for a lot of the rest of the weeks we have left, it's going to be review. I'm going to be giving you a lot of things to go back and go over kinetics and acid bases and stuff like that to be ready for that AP test in May, maybe. We'll see. I don't know. It feels like every day things are a little worse from the news, and some days that something good happens. I don't know. Whatever happens, though, know that I'm going to keep teaching chemistry the best way I can. And if you have any questions, feel free to let me know. Send me an email. I know people have been asking me a couple things here and there. But the last big topic really is right here. It's chromatography. It's not that big of a topic. I'm just going to go through the PowerPoint like I would normally and call it good. So chromatography, it goes along with the topic of intermolecular forces because this is a technique to separate a mixture into its individual components using intermolecular forces, how those molecules interact with a solvent that the molecules run through essentially. So in the picture here you can see that we've got, for example, right here, we've got this piece of paper, and it's called TLC for thin layer chromatography. And on the piece of paper, we have a sample. And that sample is this piece of leaf right here. And basically what it looks like in this picture somebody would be trying to do is they're trying to basically separate all the bits of a leaf onto this paper and just be able to see it physically, what is there in that leaf, what is in the cells of a leaf essentially. So at the very bottom here is propanone, or otherwise known as acetone, and what happens is this piece of paper soaks up the acetone, and the acetone runs through the sample here, and based on how strongly these different molecules interact with the acetone molecule, how well if they're polar with it or non-polar with it, and if they're pulled along with it or not pulled along with it, then it gets separated into these individual components here. And so things that are basically more soluble in this acetone would get carried along further along the paper, and things that are not as soluble, then they would stay near the bottom because they would not interact with that flowing acetone up the paper. So chromatography, at the end of the day, is really just this. You have a sample that is mixed into what is known as the mobile phase, and the mobile phase is the solvent that just runs through either a thin layer chromatography piece of paper or a column or something like that. And also there on the column or on the piece of paper there is what is known as the stationary phase. That's the column or the paper or whatever. It's the physical stuff that the molecules are running on or through. And basically, however strongly they interact, the molecule, the sample molecule interacts with either the stationary phase or the mobile phase, depends on how quickly it runs through the chromatography test. Excuse me. So here's just a picture here. Usually chromatography is done with a column, meaning that there's a machine and it's like a loop essentially. It's a loop of usually copper, and inside there are these little beads, through which the mobile phase will flow, and these little beads are the stationary phase. And the mobile phase is flowing through the column, and I'll do it again, the molecules that are more soluble with the mobile phase are going to flow through more quickly, and the molecules that are less soluble with the mobile phase will flow less quickly because they're not interacting with the mobile phase as well. They interact instead with the stationary phase. And if they interact with the stationary phase, then they will be attracted to the stationary phase and therefore will kind of sit on the stationary phase and not flow as far. If those molecules sit there, then they take longer to flow through and get eventually to the detector at the end of the column. So at the end of the sample trial, you have molecules which go through the mobile phase very quickly because they interact strongly with that mobile phase. They're attracted to that mobile phase. The mobile phase flows through the column. And then you have other molecules which are not attracted to the mobile phase. Instead, they are attracted to the stationary phase. So they kind of sit back and they are moving with the mobile phase because it's like a flow of water essentially. And then they come out last. So you basically separate the molecules based on how well they interact with that mobile phase, how well or how good the intermolecular forces are with that mobile phase. This is just a picture here of what a chromatograph would look like. So usually you have some sort of gas which is injected along with the column. This right here is the column. Usually this is a lot more tightly coiled. There's lots and lots of room. And basically the reason why you want a long column with a lot of coils is you want to have a lot of space for those molecules to separate away from one another. Particularly if you have a very complex sample. You guys know I worked on capsaicin. We would have basically extract from peppers, and there's a lot of junk in that stuff. So we would want to put the sample on a column, and it'd be really, really, really long, and that would allow the molecules in the different types of capsaicin, different parts of the pepper, would just take a lot longer to get through. It would take like an hour for the whole sample to pass through the column. So basically, you inject your sample here, and then it goes through the column. Everything separates based on how well the different parts of the sample interact with the mobile phase, and then it hits the detector, and then there's a computer that records it all, and you get one of these. And this is a chromatogram. A chromatogram basically gives you these peaks here, which indicate what basically indicate that you have some big peak, a big amount of something, and you can use known data, tabulated data, and lots of charts and stuff like this to tell you, oh, this is butane, or this is hexane, or this is benzene, or methylhexane. So we know what the chromatogram of these molecules looks like, and so we know where they should show up on a chromatogram. Now, on the AP test, you're never in the world going to have to look at something like this, but this would be something you would do if you go on to take something like organic chemistry. So you'll look at chromatograms, you'll work with liquid chromatographs, gas chromatographs. You'll connect a chromatograph with a mass spectrometer. The most common setup really that I've ever seen is a gas chromatograph linked up to a mass spectrometer. So you hear the phrase GCMS, gas chromatograph mass spectrometer system, and that would allow someone with a sample of unknown stuff to separate everything in it, and then you get this chromatogram, and then you pair that with the mass spectrometer, and so these peaks would be identified, would be separated. These peaks would be separated, and then it could be paired up with a mass spectrometer, so you can figure out the mass of the unknown peak. So if you had something you don't know what it is, you can really quickly figure out what its mass is, what its molecular structure is, and then you can go further and maybe run this on an NMR and figure out more precisely where hydrogens and carbons are and things like that. So there's a lot of really cool things we can do to figure out the structure and identity of an unknown compound. And really, chromatographs or chromatography, mass spectrometry, and NMR, nuclear magnetic resonance, which is not on the AP test, but these three really important processes can be used, particularly in organic chemistry, to figure out a lot of different things about compounds. So for the AP test, though, the only thing you really need to know about that is thin layer chromatography, which I showed you a little bit ago. That is the piece of paper, essentially, which acts as our stationary phase, and then the mobile phase is just a liquid. That is really weird. I didn't realize there was a sound there. I don't think I've ever played a sound, but it is what it is. So you have, oh, I'm going to turn that off. There we go. you're going to have a piece of paper that has a stationary phase on it, usually some kind of powder, and then you're going to basically have a sample put onto that piece of paper, and you'll run it like this. You'll put your sample at the very bottom, and then the mobile phase is the, in this case, the blue stuff, and that blue stuff gets absorbed up the paper, and the sample gets separated into its individual components. And this is right here known as the retention factor. RF is the retention factor, and it is equal to how far, X here, how far the different part of the sample moved up the paper divided by how far the solvent moved up the paper. So for example, this guy right here, whoa, hello Trooper the cat, that was unexpected. For example, in this one right here, Trooper, I love you, buddy, but you can't be in the video. He's down here wanting love. Sorry about that. For this one right here, let's just say that the distance traveled is 2. Hey, yeah, okay, you can go get some food. The distance the solvent went is 2, and this is 1, so the RF factor would be 1 over 2, and so it's about halfway retention factor. It's retained about halfway. So RF is the distance moved by the substance divided by the distance moved by the solvent front. So for substances that are very soluble in the liquid phase or the mobile phase, the RF will be very close to 1, because if they interact really well with that mobile phase, with the solvent, then they'll go very, very high up on the piece of paper. If the substance that is in the sample does not interact strongly with the mobile phase, then it will stick to the paper and won't move very far, so its RF will be 0. And this, again, all has to do with intermolecular forces. So if the solvent is polar, like let's say ethanol, CH3CHOH, it's got that OH at the very end making a polar molecule, and the sample has a polar component to it. I can't think of anything immediately, but just say it's some kind of polar molecule like H2S, so dihydrogen sulfide, very similar to water. It's also polar. The ethanol and the H2S are both polar compounds, so they will interact pretty strongly with each other, and so the H2S will be moved up the paper better than something that's non-polar, like a wax or a fat or hexane or something like that, so C6H10, something like that. Did I do that right? I don't think it's right, but you know what I mean. But basically, some kind of non-polar compound would not interact well with ethanol because ethanol is a polar compound. And so some non-polar species will just sit back on the paper and not be able to move up. And so its retention factor will be low, while the retention factor of something polar in an ethanol solvent is going to be moved up further the paper. And that is really it. That is actually it for this discussion.